Good day, ladies and gentlemen. We are welcome to our lecture number 2 on Chen723, which is basic electronics. In our first lecture, we introduced different types of materials, conductors, semiconductors, and insulators. And we have talked about semiconductors, how they are created. We have what we call intrinsic, which is the pure, and we also talked about the extrinsic, where we introduce pouring materials to group 4 elements. If you introduce group 5, you have N type, and if you introduce group 3, you have P type. So today we are going to look at what we call PN junction diode. It is a device that has two terminals. One terminal is doped with group 3 element as shown here, and for this we have P type material. The other end is doped with group 5 element, and for this reason we have N-type material. Remember what we have seen in our lecture number 1. So the two terminals, one is called the anode and the other one is called the cathode. And this device, that's the diode, it has two electrodes. The electrode means terminals. One end is the anode and the other one is the cathode. And of course, this device conducts only in one direction, allows the current to flow only in one direction, that is from the anode to the cathode, but it will not allow the reverse. So we call it a unidirectional device because it only flow in only one direction. And for this reason, the diode has a property of rectifying a voltage. What we mean by rectifier, we are going to see very soon, is that device that will take alternating current and change it to flow in only one direction. So diode allows the flow of current in only one direction, and for this reason it is called a rectifier diode. Now, if the anode of the diode, as we have seen here, if you apply a positive electricity here on the anode, and on the cathode you apply negative electricity, you can see that P type has what? Positive majority. So this positive applied here will be pushing them according to law of electricity, like charges repel. And the negative I put here will now be pushing these electrons so that they will start crossing this junction. And whenever this happens, we say our diode is forward bias. On the anode we put positive, on the cathode we put negative, and so the charge carriers, the electrons and the holes, will start crossing this. Therefore, whenever there is flow of charge carriers, we have a current flowing, and this kind of orientation we call it forward bias. But if we change the anode with a negative terminal of our battery and the cathode with the positive, let's go back to the diagram. If you put negative here and you put positive here, we know the negative and this P positive will be attracting one another, and here the positive and this N type, which is negative, will be attracting one another. Therefore, my charge carriers will be moving backwards. Instead of crossing this junction, they will be moving backward, and for this we call this configuration a reverse bias, and it is the condition under which the current will not be flowing and the diode is now in the cut-off condition. Now, when you forward bias it and allow the current to flow, the amount of current is given by this formula. ID, that is the diode current, is equal to I naught. We call this one reverse saturation current. That is the current that will flow even if we reverse bias diode. It is very, very small. Everything times exponential of Q Vd all over nkt, where Q is the charge of electron, which is 1.6 times 10 raised to power minus 19 coulomb, and the Vd is the voltage applied from our battery source. N is a constant and its value is between 1 and 2. K is Boltzmann's constant, and T is our absolute temperature in Kelvin. So further explanation about this diode operation, as we have seen before, or let me go back to the diagram here. Whenever you apply forward bias, here we put positive, here negative. I told you they will be pushing charge carriers crossing this junction and the current will start flowing. But we need to know that at the origin, that is when the voltage is 0, no flow of electricity. And as it keep on increasing, still no flow until you reach a minimum value. We call this one cut-in voltage or turn-on voltage. It is the minimum voltage under which the electrons and the holes will start crossing this junction and our current will now start increasing exponentially. So further to this, if you look at this diagram, the two materials that are commonly used for producing semiconductor diodes and other things, they are either germanium and silicon. So for germanium, you need only 0.2 volt as your cut-in or turn-on voltage. But for the silicon, you have to supply around 0.7 before it starts increasing exponentially. But in the reverse direction, we have said whenever we reverse bias it, ideally we're supposed to have no current flowing. So that's why you're seeing for all this long distance, the curves are along the zero line. But if you keep on pressing it, it will reach a point that we call a breakdown voltage. That is the voltage that will force the diode to start conducting in the reverse direction because of the pressure of the electricity applied to it. And whenever that happens, the diode is completely damaged. And this turning point at which the breakage takes place, we call it the knee. And the amount of current that is flowing before the breakage, we call it the leakage current, which is our I naught we have seen in that formula. So the diodes in this case, they are exhibiting what we call Zener or avalanche breakdown effect, and it is a point that actually when diodes break down, it is damaged, except in some applications that we may look at later. So now we considered, we have seen a diode. It has two terminals, one is positive P type and the other one is N type, and we have seen that we can forward bias it and what, reverse bias it. So when it is forward bias, current will flow. When it is reverse, no flow of current. So now we are going to see some applications of diode. The first application of the diode, it is used in rectification. And what we mean by the word rectification is simply this. This is my AC current, which is alternating with time. So it is flowing in the positive, negative continuously. So rectification is a process of allowing that alternating current to flow only in one direction, either in the positive only or in the negative only. So here we are using single diode to achieve that, and that is why we call it half wave, because it is single diode, you will see. So when you supply your AC to this transformer, the function of the transformer is to reduce the voltage. Mostly we reduce it to around, let's say 12 volt, 15 volt, 9 volt, depending on what I need. So when the positive comes here, it will forward bias this diode, and for this, the positive will now flow through the diode to the load. But in the negative half cycle, this will be negative, and therefore the diode will be a reverse bias. It will not conduct. So everything is break. It is blocked, nothing flow. It is like wasted. Now after this negative, it will also go back to positive, and that positive will forward bias the diode and allow the current to flow. It will keep on doing like this. And if you look at it, we are conserving the positive half and we are destroying what? The negative halves. And this is the reason why we call this one a half wave rectifier. So as I already explained, it accepts as input input voltage from our step down transformer. That is a transformer that can take 240 from our PHCN supply and maybe reduce it to 9, 15, 12, something like this. So if it does that, you give only one directional output, as I have illustrated here. Only the positives are allowed to flow, and this is called half wave. And I told you the reason is because half of the cycle, the positive, we preserve it, and the other half we destroy it, we block it. That is why we call it half wave. The second type is what we call full wave rectifier, and this one, instead of using only one diode, it is using two diodes which are connected in series to our load resistor. Look at the diagram. This is my transformer, and this transformer is called center tap because at the middle we have another terminal that is tapping signal to our load. So what happens here is this: when the electricity comes, the first half cycle, A will be positive and this B will be negative. Therefore this diode will be forward biased and this one will be reverse biased. Therefore this will allow the first half cycle to flow. And when it's changed to negative, A will be negative and this will be positive. For this diode will now conduct again. So if you look at this one, we conduct both the positive and negative, but the only difference is that we don't allow the signal to keep on oscillating. It will be flowing in the same direction. All these halves, they will be maintained. So the full wave rectifier is a better option because it allows all the signal to pass, but instead of flowing in two directions, it will only flow in one direction. And we call this one full wave because none of the half waves is wasted. All of them are conserved, but we change them from flowing in two directions to flow in only one direction. So the next thing is what we call light emitting diode. These light emitting diodes, they are the diodes that gives out light as the output energy when they are connected to electricity. And of course, they are made using PN junction material. That is the P-type semiconductor, and this is the what? N-type semiconductor, and they are what? Connected together to form this junction. So this is your battery. This is the positive terminal and this is the negative terminal. What happens is this: whenever you supply this positive, it will push the holes toward the junction, and this negative will push electrons toward the junction. And for this reason, the flow of current will start. And these electrons, when they get higher energy from this battery, they will now move from their a low state or ground state energy level to the what? Higher state energy level. If you can remember your electronics configuration, around the nucleus we have different shells, so it will jump from the lower shell into the what? The higher shell, because of the energy absorbed from this battery. But even if it goes there, it will never remain there for a long time. It will come back to its original position, that's the ground state position. And in doing this, it has to release the energy it absorbed, and that energy comes out in form of what? Light. So this is what we call light emitting diode. The light emitting diode is used in different applications. For instance, it is used in display systems. Look at our advertisement boards. Look at our shops. We put all these kind of diode to be what? Blinking on and off to give different colors and for attraction, of course. We use it in optical fiber communication. Our GSM companies, we have been maybe seeing them digging and burying a cable, and that cable, we call it optical fiber cable, and it contains light emitting diode in it. And also we use it in infrared remote control. Everybody that has a TV and satellite at home, we actually use remote control device to choose our station, to on and off our TV and other things like that. In that application also we are using light emitting diode. In traffic lights, everybody knows red means stop, green means move, and the yellow or amber means get ready. So all of them are light emitting diodes, and they are used in this application. We also use it in security alarm systems. For instance, if you have a system that whenever somebody crosses a place, it will detect and raise an alarm, we use light emitting diode for that. We also use it in digital watches. Our watches that have a light emitting diode are the ones that if you press in the night, it will give you the screen to take your time. We use them in also camera flashes. Whenever you are snapping picture, it comes with what? A flash. And in that application, still we are using what? The light emitting diode to give us that flashing light. Then it is used currently or recently in automotive headlamp. Many of our modern cars, they have light emitting diode as their head lamps. Now that is about the diodes. Another component that is fabricated using semiconductor materials is called bipolar junction diode. And the bipolar junction diode it has three terminals: NPN, that is negative type, positive negative, or PNP. P posed in the middle, N, and at the other end P. And the terminals, the three terminals it has, one is called emitter, the other one is called base, and the last one is called collector. Look at the diagrams here. This is my emitter with the arrow pointing out, and this is my collector, and this is my base. And if you look at this one also, my emitter, but the arrow is pointing in, I have my collector and I have my base. So what's the difference between these two? Whenever you see the arrow pointing out, we say this is NPN type of transistor. But if the arrow is pointing in, we call it PNP transistor. And this type of material, it is used for different applications. But before seeing the applications, let us see how we can operate them. So if you want to operate the NPN diode, transistor, this is my N, this is my P in between the two, and this is the other end, which is what? The N-type semiconductor material. So I have two batteries. If you look at this, my negative terminal of this battery goes to N, and my positive here goes to the other N, but in the middle I have my P, which has the two other terminals of the battery. So if you supply these two voltages to the NPN transistor, what happens is it will exhibit a property like this. That is, you need to start applying IB, that is the current through the base, as small as possible. You keep on increasing until the transistor start working. And if it start working, we can have a graph like this. Anything that is within this range at the lower level, we call it cut-off region. And this cut-off region is a place where the amount of base current we are supplying to this transistor is not enough for it to start conducting. So therefore the transistor is off in that condition and it is not conducting. So as you keep on increasing your base current here, you reach a point where the transistor will start conducting. And as you increase it from around 0.2 milliampere to 0.8 milliampere, it will still be conducting, and we call this active region. But whenever you go beyond this, then it will start operating as if it is what? A superconductor. It doesn't have any resistivity, therefore the current will flow without any control, and that is the upper region here, and we call this one a saturation region. Let me repeat. When the base current is very small and the transistor is not conducting, we call it to be in what? We say it is in what? Cut-off region. When the base current is enough to make the transistor start conducting, ranges from 0.2 to 0.8 milliampere, we call that active region. And whenever you go beyond that base current, it will start conducting as if it doesn't have any resistivity, and that region we call it what? Saturation region. And this is the circuit configuration for NPN, and this is the circuit configuration for what? PNP. Let me repeat. I said this NPN means I'll bring N-type semiconductor, I'll bring another one at the other end, and in between them I'll put P-type semiconductor. So I call it NPN just by the arrangement, and here I call it PNP just by the arrangement. And here we have seen three regions of it. What? Operation. Cut-off region when the base current is very small, active region when the base current is enough for transistor start conducting from 0.2 up to 0.8 milliampere, and we have saturation region when the current is too much, is flowing as if the transistor is ideal conductor without any resistance. So the next thing we should learn about the transistors, that is bipolar junction transistor BJT, is that it can also be configured, it can be arranged, it can be connected in three different configurations. The other one we have seen, the agents of operation, cut-off, active, and saturation. But here is a configuration, that is the method of connection. We have what we call common emitter, we have what we call common base, and we have what we call common collector. Let us look at them one after the other. Look at this diagram. The arrow is pointing out, therefore it is NPN, as I've already explained. This is my source of electricity, and this is another source of electricity. And the terminal of this source, one goes to the emitter and the other one goes to what? The collector. And this source also, one terminal goes to the base and the other one goes to collector. So you can see these two supplies, the output and the input, all of them are connected to the collector, and this is what we call common collector configuration. Now if you understand this, let's go to the second one. If you look at this, this is my transistor, and this is my input supply, and this is my output supply. You can see that one terminal of the output is connected to collector, the other one is connected to the emitter. Also, if you look at the input supply, one terminal goes to the base and the other one goes to emitter. So we can see that the output and the input, all of them are connected to the emitter, and we call this one common emitter configuration because it is common to the input and what? The output. So if you look at this, this is my base. It is common to the input and it is common to the output. So this one is called common base configurations. These are the three basic connection configurations of what? Transistor. Common emitter, common collector, and what? Common base. So the next thing is we are going to see the parameters, the specifications of any transistor which is connected in either common base or common emitter or common collector. If we look at the input impedance, that is the amount of resistance that is created whenever you are delivering signal into the base of the transistor, for common base is low, for common emitter is medium, and for common collector the input impedance is very high. We need to remember this. For output impedance, for common base is very high, for common emitter is high, and for common collector is low. Then we have phase angle. What we mean by phase angle is the angle between the current and the voltage. Are they reaching maximum and minimum at the same time? If yes, then the phase angle is 0. But if they are not reaching maximum and minimum at the same time, we say we have a phase angle, and that phase angle ranges between 0 to 360. So the common base, the phase angle is 0, which means the current and voltage are reaching maximum and minimum at the same time. But for common emitter, they have a phase angle of 180. That is, when the voltage reaches maximum, it will take 180 degrees before the current reaches the same position. But for the common collector, it is also 0. The voltage gain, that is the ratio of the output voltage to the input, is high for common base, medium for common emitter, and it is low for common collector. Then the current gain, that's the ratio of the output current to the input current. For common base is low, for common emitter is medium, and for common collector is high. Finally, the power gain, that is the power output over the power input. For common base is low, for common emitter is very high, and for common collector is medium. So what are we saying here? Whenever you are concerned with voltage gain, you need voltage to be high, you use what? The common base. When you need a current gain to be high, you use what? You use common collector. And if you want to have a gain of power very high, you use what? Common emitter. This is the meaning of this table. So the next thing is the operation parameters from the manufacturer's datasheet. That is, whenever I go to a seller, I want to buy any transistor for an application, they will give me, and of course I can have access to what they call datasheet. This datasheet will give you information about some parameters. The first one is the voltage between collector and emitter, BCE, will be given. The collector base voltage, BCB, is also given. Emitter base voltage, BEV, is also given. Collector current, IC, is given. Power dissipation, PD, is given. Operating temperature, the maximum temperature that our transistor can tolerate, is given. An amplification factor, that is the ratio of the output to input, is also given, and this will help you to make decision on which one are you going to choose. And of course, it will help you to know when you are designing a circuit with using that transistor, you know all these parameters. It will help you in doing your calculations. And the next thing is, what are the applications of the transistor? The transistor has so many applications, but the most common are: number one, amplification. What we mean by amplification, if you look at our public address systems, in our mosques, in our churches, in our ceremonial places, we use public address system. You speak into the mic and we have a higher volume of you're speaking through what? The amplifier. So this is done using what? A transistor. And then there is an oscillator. The oscillator is something that will take a DC input and produce what? An output as an AC. For instance, all the sirens on the vehicles of our governors and what have you, the police, fire service, they are all made using oscillators, and these ones are called audio oscillators because we can hear them. We have radio or modulate oscillators, which have a very high frequency beyond our hearing. The next application of the transistor is this use in modulation. Modulation is just a process of combining two signals of different frequency. In communication, we do that. For instance, the signal or the broadcast from any radio or TV station, it went through this process. The let's say the original speaking of whoever is speaking is now combined with a higher frequency. We call it a carrier frequency. So when they are combined, we can now propagate it in the free space in air, and transistor is used for that application modulation. And the last one, we use a transistor for switching. Switching simply means to turn on a system or to turn it off. We use a transistor for that application. So at this point, ladies and gentlemen, thank you very much for your time. I advise you, as usual, to watch this video over and over again. It will help you understand better. If you have any issue, any concern, you can contact me for clarification. Thank you very much. We'll meet in our next lecture.